So here's our first demo of doing binary I/O. You notice a bunch of imports at the top: file input stream, file output stream, and of course I/O exception, because we're going to have to potentially throw an I/O exception. Remember, this is a checked exception, so we have to deal with it either with an appropriate try-catch block, which we haven't done in here. Now don't be fooled by the fact that you see try here. These are not try-catch blocks. You understand that, right? Because this is a try with resources construct. That's something else. So we don't have any try-catch blocks here, which means we have to declare that we throw the exception, because it is a checked exception, which means we can't just ignore it. So we are using a try with resources here, which means we're just going to open those things up, these resources up here and here. One is going to be opening a file for output. That's on the top section here, and down here we're going to open that same file that we've created, this time for input, and we don't have to close it because it's in a try with resources. So that means when we finish using it, it'll automatically close all by itself, so we don't have to worry about it. So what are we doing in each of these cases? Well, in the first case, you'll notice that we open a file for output, and we call this file stream output, but the name of the file is temp.dat. So remember that, because we're going to find that file in a directory, a folder, and look at it and see what's there. We're going to write out to it a bunch of bytes. So in a for loop that iterates 10 times, with I going from an initial value of 1 through 10, because it's less than or equal to 10. So it's going to go all the way up to 10 from 1. It's going to write 10 bytes to this file. When I do an output.write, then it's understood that I'm writing bytes, and I, although it be an integer, is going to be written as a byte to my output file. After writing those 10 bytes from 1 to 10 to the file, I'm going to then open that file, same file, temp.dat, and notice when I created the file up here, I did not have a Boolean argument. If I did, it could be true or false. If it was false, it's equivalent to what I have here. If it was true, it would mean I would want to append to an existing file, potentially. In any case, you don't see a second argument here, so you know that I will overwrite. In other words, if there is a file called temp.dat already there, I'm going to erase it and recreate it. In any case, I open that file up after I've written the bytes from 1 to 10 to it, and then I read the bytes one at a time. Notice that value is declared to be an integer, but I'm still reading bytes from the file because that's how this works. So I say value equals input.read, and again, the reason I want to declare value to be an integer is because it's the only way I can get that -1 as an integer value, as opposed to the bytes 0 to 255. It's the only way I can get that -1 to indicate that I've reached the end of the file, and in fact I haven't read a byte at that point. I ran out of bytes. That's what reading -1 means. So while I haven't read -1, in other words, while there are still bytes in the file, I'm going to continue looping and reading, and every time I read something, I'm going to output that value concatenated with a blank. In other words, I'm going to write a blank delimited list of all the bytes that I read from that file. So I already ran it, as you can see at the bottom, but let me clear that off for you so you can see it run for yourselves. So I just clicked on run, and it ran, and it generated 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now, this isn't particularly instructive in some ways, because you don't really know what went into the file. What proof do I have that this wasn't just a regular run-of-the-mill text file? How do I know that it didn't write the printable digit 1 and then the printable digit 2 and so on and so forth? How do I know that it actually wrote bytes to the file? Well, I don't from looking at this demo, unfortunately. But what we can do is find this file temp.dat, and we can examine it to see what actually happened there. So I'm going to go over here, and I'm going to show in System Explorer, and I'm going to, well, that's not where we should be, so just bear with me for a second. We'll find the right place. And we are getting there. Okay, so here is the file that I created, temp.dat. Now let me open it for you in Notepad++. Now Notepad++ is kind of interesting because it will show us things that are not regular printable characters. And there's what it did. So you see these funny looking things, SOH, STX. You could look all these up in an ASCII character table and find out what they mean. We have 1, 2, 3, 4, 5, 6, 7, 8, and we actually wrote 2 more things. Why are they not visible, do you suppose? Well, we'll talk about that in a minute. Let's talk about some of these codes that we see here. Some of the codes, as you go through a computer science program, you'll get used to them and you'll know what they mean. For example, the bell code, which you see right here, BEL, that's the, or terminal beep sometimes it's called, that's code 7. And you can see that we have 1, 2, 3, 4, 5, 6, 7. 8 is the code for backspace, and you can see there's a BS, which stands for backspace. That one you might not learn about, but you might learn that the code for tab is 9. And look where the cursor goes here. If I click way over here, you see all that white space between the BS, which is backspace or code 8, and here where the cursor is after I click, there's a bunch of white space in here. What do you suppose that is? That's the tab character, and the code for tab is 9. Now 10 happens to be the code for the new line character, which traditionally means we move down 1 line. And that's what we've done. Notice there's 2 lines in this file. So that sheds a little bit of light on what's actually being stored in this file. Now let's go a little bit further with this and push this a little bit harder. I'm going to change the demo. Do you remember what we said a number of slides ago? We showed some ASCII codes for decimal digits, and I don't know how good your memory is, but there was a hexadecimal value. 0x31 represented the digit 1, and that was 3 groups of 16, which is 48. So what do you suppose would happen way back here in this source code if I change this to 48? And let's go all the way up to, well, I want to go 48, 49, 50, 51, 2, 3, 4, 5, 6, 7. So I want to go all the way to 57. Now think carefully about what I'm doing here and watch what happens when we rerun this program. Okay, so I'm going to clear off the bottom here. I'm going to rerun the program. And not surprisingly, now it's an extra byte this time, right? I've actually written out a total of 10 bytes this time. Well, I guess I did last time too, so it's still 10 bytes. But this time they go from 48 to 57. And not surprisingly, when I read them back in this section of the program, we still see those same 10 bytes, 48, 49, 50, all the way up to 57. But let's have a look at the text file, or sorry, the file. I shouldn't say text file because it's a binary file. Let's have a look at the binary file and see what it contains. So I'm going to reopen this same file in Notepad, and you might be a bit surprised at what you see this time. So let's go in here, and here, and here, and here, and in we go, and to our demo. So here we are, same size, and let's go ahead and open it again in the same editor. Oh, well, look at that. What do you notice now? Instead of those funny looking codes, we see the printable digit, the visible digit 0 and 1 and 2 and 3, and those are the 10 bytes that got written to the file this time. Okay, those were the bytes 48, 49, 50. So what is this? Is it a text file or is it a binary file? Well, it all depends on your perspective and what you were expecting and what your intent was, doesn't it? Somebody opening this file would look at it and say, oh, look, it's a text file. It contains the printable digits 0 to 9. But we know better because our intent was that that be a binary file containing the bytes 48, 49, 50, and so on. So that's the different perspective I wanted to give you that I don't think was clear in the way the author describes things. It gives you a little bit more depth to what's going on here. Perhaps in some ways it muddies the water because maybe it starts to get not so clear that we're writing binary data. But in fact, that's where you do want to focus. This whole chapter is on binary I/O, and we are writing raw bytes. They happen to go 48, 49, all the way to 57. And if that happens to look like this inside the file, well, that's how it turned out. Nevertheless, our intent was that this is raw binary data. And that, I guess, is the end of this demonstration.